lecture I will start diffraction of light. Here first I will explain what is diffraction and then I will describe single slit and double slit diffraction pattern. Diffraction is defined as the bending of waves around an obstacle or spreading of waves when they pass through a narrow opening. To explain the diffraction of light wave, let us consider a plane wave incident on a long narrow slit of width b. According to geometrical optics, we expect the region AB of the screen SS prime to be illuminated and the remaining position known as geometrical shadow to be absolutely dark. However, if the observations are made carefully, then we find that if the width of the slit is not very large compared to the wavelength of light, then the light intensity in the region AB is not uniform and there is also some intensity inside the geometrical shadow. Further, if the width of the slit is made smaller, larger amounts of light reach in the geometrical shadow. This spreading out of a wave when it passes through a narrow opening is known as the phenomenon of diffraction, and the intensity distribution on the screen is known as diffraction pattern. Like interference, this phenomenon can be explained satisfactorily by assuming a wave character for light. We will see that the spreading out decreases with decrease in the wavelength. Since the light wavelength are very small, the effects due to diffraction are not easily observed. On the other hand, sound waves have wavelengths comparable to ordinary objects and are diffracted by them. Due to this, we hear sound even though we may not be in a direct line to their sources. In case of light, the diffraction phenomena are usually divided into two classes: Fresnel diffraction and Fraunhofer diffraction. In the Fresnel class of diffraction, the source of light and the screen are in general at finite distance from the diffracting aperture or slit as shown in this figure. On the other hand, in the Fraunhofer class of diffraction, the source and the screen are at infinite distances from the aperture or slit. In the laboratory, this is easily achieved by placing the source on the focal plane of a convex lens and placing the screen on the focal plane of another convex lens as shown in this figure. The two lenses effectively move the source and the screen to infinity because the first lens makes the light beam parallel and the second lens effectively makes the screen receive a parallel beam of light. Now, I will describe the single slit diffraction patterns due to an infinitely long slit of width b. Let us assume a plane monochromatic wave is incident normally on the slit. Now, we want to calculate the intensity distribution on the focal plane of the lens L. When a plane wave front of monochromatic light of wavelength lambda is incident normally on the plane of the slit, its size is limited at the instant it occupies the plane of the slit. Now, according to the principle of Huygens-Fresnel, at this instant every point of the wave front in the plane of the slit is to be regarded as the origin of secondary spherical wave fronts, which spread out to the right in all directions. The part of each wavelet travelling normally to the slit are brought to focus at P naught by the lens, while the parts travelling at an angle theta with the normal are brought to focus at P on the screen. So, we can assume that the slit consists of a large number of equally spaced point sources and that each point on the slit is a source of Huygens secondary wavelets which interfere with the waves emanating from other points. Let the point sources be at A1, A2, A3 so on, and let the distance between two consecutive points be delta as shown in this figure. Thus, if there are n point sources on the slit, then B will be equal to n minus 1 delta. We will now calculate the resultant field produced by these n sources at the point P which receive parallel rays making an angle theta with the normal to the slit. Since the slit actually consists of a continuous distribution of sources, we will in the final expression let n goes to infinity and delta goes to 0 such that delta into n tends to B. Now, at the point P, the amplitude of the disturbance reaching from A1, A2, A3 so on will be very nearly the same because the point P is at a distance which is very large in comparison to B. However, because of even a slightly different path lengths to the point P, the field produced by A1 will differ in phase from the field produced by A2. For an incident plane wave, the points A1, A2 etc. are in phase and therefore, the additional path traversed by the disturbance emanating from the point A2 will be A2 A2 prime, where A2 prime is the foot of the perpendicular drawn from A1 on A2 B2. This follows from the fact that the optical paths A1 B1 P and A2 prime B2 P are the same. If the diffracted rays makes an angle theta with the normal to the slit, then the path difference A2 prime would be delta sin theta and the corresponding phase difference phi would be 2 pi by lambda into delta sin theta. Thus, if the field at the point P due to the disturbance emanating from the point A1 is A cos omega t, then the field due to disturbance emanating from A2 would be A cos omega t minus phi. Now, the difference in the phases of the disturbance reaching from the point A2 and A3 will also be phi and thus the resultant field at the point P would be given by A cos omega t plus A cos omega t minus phi plus A cos omega t minus 2 phi up to plus A cos omega t minus n minus 1 phi, where phi is equal to 2 pi by lambda into delta sin theta. So, here we have to find the resultant of n simple harmonic waves all having the same amplitude and with their phases increasing in arithmetic progression. This can be obtained by using geometrical method discussed in the first lecture of interference of light. We can show that cos omega t plus cos omega t minus phi up to plus cos omega t minus n minus phi equal to sin n phi by 2 divided by sin phi by 2 into cos omega t minus 1 by 2 n minus 1 phi. Thus, the resultant field at point P becomes equal to E theta cos omega t minus 1 by 2 n minus 1 phi, where E theta equal to A into sin n phi by 2 divided by sin phi by 2, and A is the amplitude of each wave. Here we can show that n phi by 2 will be equal to pi by lambda into n into delta sin theta, which we can write equal to pi by lambda into b sin theta, and therefore phi by 2 will be equal to pi b sin theta divided by lambda into n. In the limit of n tending to infinity, phi by 2 will be very small. So, we can write sin phi by 2 approximately equal to phi by 2, and we have resultant amplitude E theta equal to n times A sin pi b sin theta by lambda divided by pi b sin theta divided by lambda. This we can write equal to capital A into sin beta by beta, where capital A equal to n times A and beta is equal to pi b sin theta by lambda. So, the resultant field at the point P becomes equal to A sin beta by beta cos omega t minus beta. Thus, the resultant vibration is a simple harmonic, and the amplitude of this varies with angle theta. Since the position of point P depends on theta, the amplitude of the resultant vibration will vary with the position of point P on the screen. The intensity of the resultant vibration is given by I equal to I naught sin square beta by beta square, where I naught is equal to capital A square, which is equal to n square into A square, and this represents the intensity for theta is equal to 0. That is, intensity of the resultant vibration of the waves travelling in a direction perpendicular to the plane of the slit. In this case, all waves will arrive in phase at point P, resulting maximum intensity of the resultant wave. Now, I will discuss positions of maxima and minima on the screen. We have intensity of the resultant wave I equal to I naught sin square beta by beta square. So, the intensity will be 0 in the diffraction pattern at the position where sin beta is equal to 0, that is beta is equal to m pi, where m is equal to plus minus 1, plus minus 2, plus minus 3, so on, but m should not be equal to 0. And when beta is equal to 0, we have sin beta by beta equal to 1 and I is equal to I naught, which correspond to principal maximum intensity. And the condition for minima is beta is equal to pi b sin theta by lambda equal to m pi, and the condition for principal maxima is beta is equal to 0. So, for minima we have b sin theta is equal to m lambda, where m is equal to plus minus 1, plus minus 2, plus minus 3, so on. So, the first minimum occurs at theta is equal to plus minus sin inverse lambda by b, and the second minimum will occur at theta is equal to plus minus sin inverse 2 lambda by b, etc. Since sin theta cannot exceed unity, the maximum value of m is the integer which is less than or equal to b by lambda. The position of minima can be explained by simple qualitative argument. Let us consider the case m is equal to 1. The angle theta satisfy the equation b sin theta is equal to lambda. Now we divide the slit into two halves as shown in this figure. Consider 2 points A and A prime separated by a distance b by 2. Clearly, the path difference between the disturbance emanating from A and A prime is b by 2 sin theta, which in this case is lambda by 2. The corresponding phase difference will be pi and the resultant disturbance will be 0. Similarly, the disturbance from the point B will be cancelled by the disturbance reaching from the point B prime. Thus, the resultant disturbance due to the upper half of the slit will be cancelled by the disturbance reaching from the lower half and the resultant intensity at point P will be 0. In a similar manner, when b sin theta is equal to 2 lambda, we divide the slit into 4 parts, the first and the second quarter cancelling each other and the third and fourth quarter cancelling each other. Similarly, when m is equal to 3, the slit is divided into 6 equal parts and so on. Now, let us find out the position of secondary maxima. So, we have intensity I is equal to I naught sin square beta by beta square. So, in order to determine the position of maxima, we differentiate this equation with respect to beta and set it equal to 0. Thus, d I by d beta will be equal to I naught 2 sin beta into cos beta divided by beta square minus 2 sin square beta by beta square, and this we have to equate to 0. And after simplification, we will get d I by d beta is equal to 2 I naught sin beta by beta into beta cos beta minus sin beta upon beta square is equal to 0. So, here either sin beta is equal to 0, this will gives beta is equal to m lambda, where m is not is equal to 0. This correspond to minimum intensity. The condition for maxima are roots of the equation beta cos beta minus sin beta is equal to 0 or beta is equal to tan beta. The roots of this equation can be found by determining the position of intersections of the curves y is equal to beta and y is equal to tan beta as shown in this diagram. The intersections occur at beta is equal to 0 and beta is equal to 1.43 pi and beta is equal to 2.46 pi etc. The root beta is equal to 0 correspond to the central maxima, and for this we have I equal to I naught. The other roots like beta is equal to 1.43 pi, beta is equal to 2.46 pi etc. give the position of first maxima, second maxima, so on. So, intensity of principal maxima as we have seen is given by I is equal to I naught. So, for the first maxima we have beta is equal to 1.43 pi. So, putting this value of beta in the intensity equation, we get the intensity of first maxima equal to I naught into sin 1.43 pi divided by 1.43 pi whole square. So, this comes out to be 0.0496 I naught. Thus, the intensity of the first maxima is about 4.96% of the central maximum. Similarly, intensity of second maxima is 1.68% of the principal maxima I naught. Thus, the intensity of the principal maxima is about 20 times as great as that of the first secondary maxima. Secondary maxima are very feeble and their intensities diminish very rapidly as shown in this figure. This table describes the intensity of various secondary maxima, and from here we can again see that most of the light is concentrated only in the principal maxima. Now, let us find the width of the principal maxima. So, we have beta is equal to pi b sin theta by lambda, and for first minima beta should be equal to plus minus pi, or pi b sin theta by lambda is equal to plus minus pi. From here we have sin theta is equal to plus minus lambda by b, where b is the width of the slit. So, from this equation we see that the spread of the principal maxima is inversely proportional to the width of the slit b. If we take b is equal to lambda, then sin theta will be equal to plus minus 1, or theta equal to plus minus pi by 2. That is, the first minimum occur at 90 degree with the normal. Under this condition, the light after traversing the slit is spread out in all directions with an intensity which decreases steadily as theta increases. There are no maxima and minima. If we take beta less than lambda, then for first minimum b sin theta should be equal to plus minus lambda, and sin theta equal to plus minus lambda by b, which will be greater than 1 if b is less than lambda, which is impossible. Therefore, I is equal to I naught sin square beta by beta square does not hold when the slit width b becomes less than 1 wavelength. Further, if theta is very small, we can write sin theta approximately equal to theta. So, half width of the principal maximum delta theta will be approximately equal to lambda by b. In the limit of lambda tending to 0, delta theta will be tending to 0, and the diffraction effect will be completely absent. Here it should be noted that the spreading is only in the direction of the width of the slit, not in the direction of length of the slit. This is because of the fact that length of the slit is very large compared to its width. Thus, when a beam of parallel monochromatic light is incident normally on a opaque plate in which there is a long narrow slit, the transmitted beam is spread out in a direction perpendicular to the length of the slit. So, when it is focused on the screen by a lens, single slit diffraction pattern is observed, which consists of central bright band much wider than the slit width, situated directly opposite to the slit and bordered by dark and bright bands of decreasing intensity. The central bright band is extremely intense and its width is approximately twice as great as that of Fenter side bands. So, this finishes the description of single slit diffraction patterns, and now I will discuss the diffraction at a circular aperture. So, if we replace single slit as we have discussed in previous discussion by a circular aperture, then the diffraction pattern is consisted of a bright disc called Ayres disc, surrounded by a number of concentric alternate dark and bright rings of rapidly decreasing intensity as shown in this figure. I will not discuss here the detailed theory of diffraction at circular aperture, but on the basis of theoretical calculation it can be shown that the angular radius of the first dark ring is 1.22 lambda by d, where d is the diameter of the circular aperture and lambda is the wavelength of the monochromatic light. This may also be taken as the angular radius of the bright central disc. About 84% of the transmitted light energy is concentrated in the central bright disk. This result we will use later to calculate the resolving power of telescope and microscopes. So, now let us discuss the diffraction pattern of double slit. So, here let us consider two parallel slits, each of width b and separated by a opaque region of width a as shown in this figure. Now, we will study the diffraction pattern produced by two slits when a beam of monochromatic light of wavelength lambda is incident normally on the plane of the slits. Like single slit, let us consider that both slits consist of a large number of equally spaced point sources and that each point on the slit is a source of Huygens secondary wavelets. Let the point sources be at A1, A2, A3 etc. in the first slit and B1, B2, B3 etc. in the second slit. We assume that the distance between the two consecutive points in either of the slit is d is equal to A plus B. If the diffracted rays make an angle theta with the normal to the plane of the slits, then the path difference between the disturbance reaching the point P on the screen from two consecutive points in a slit will be d sin theta. The field produced by the first slit at the point P will therefore be given by E1 is equal to A sin beta by beta cos omega t minus beta. Similarly, the second slit will produce a field E2 is equal to A sin beta by beta cos omega t minus beta minus phi at the point P, where phi is equal to 2 pi by lambda into A plus B sin theta or phi is equal to 2 pi by lambda into d sin theta, where d is equal to A plus B. Phi represent the phase difference between the disturbance reaching the point P from two corresponding points on the slits. By corresponding points, we imply pair of points like A1 B1, A2 B2 so on the slit which are separated by a distance d is equal to A plus B. Therefore, the resultant field at P will be equal to E1 plus E2, and so now substituting the value of E1 and E2, we get the resultant field at the point P E equal to 2A sin beta by beta cos phi by 2 into cos omega t minus beta minus phi by 2. If we define gamma is equal to phi by 2 equal to pi by lambda into d sin theta, then the resultant field E will be equal to 2A sin beta by beta cos gamma cos omega t minus beta minus gamma. So, the intensity of the resultant field at P will be equal to 4A square sin square beta square divided by beta square into cos square gamma. Here A square is equal to I naught, then I will be equal to 4 I naught sin square beta by beta square into cos square gamma, where gamma is equal to pi by lambda into A plus B sin theta and beta is equal to pi by lambda B sin theta. So, this equation describes the intensity of double slit diffraction pattern on the screen. In this expression, I naught sin square beta by beta square represent the intensity distribution produced by one of the slits. The intensity distribution is a product of two terms. The first term sin square beta by beta square represent the diffraction pattern produced by a single slit of width b, and the second term cos square gamma represent the interference pattern produced by 2 point sources separated by a distance a plus b. If the slit width are very small, so that there is almost no variation of term sin square by beta square with theta, then we simply obtain the Young's interference pattern. Now, let us discuss the dependence of intensity on I naught sin square beta by beta square term, that is single slit intensity pattern. The intensity I is 0 whenever this function vanishes, that is when sin beta is equal to 0, that is beta is equal to plus minus m pi, where m is equal to 1 to 3, but m is not is equal to 0, or b sin theta is equal to plus minus m lambda. So, whenever this condition is satisfied, the intensity in the diffraction pattern of double slit will be 0. Now, the position of maxima due to this factor are at beta is equal to 0 and at value of beta approaching to plus minus 3 pi by 2, plus minus 5 pi by 2, plus minus 7 pi by 2, etc. Now, let us discuss the dependence of intensity on cos square gamma term. The position of maximum intensity due to this factor are given by those value of gamma for which cos square gamma is equal to 1, or where gamma is equal to pi by lambda into a plus b sin theta. So, cos square gamma will be 1 when gamma equal to plus minus n pi, where n is equal to 0, 1, 2, 3, so on, or a plus b sin theta is equal to plus minus n lambda, again n is equal to 0, 1, 2, 3. This is the condition for maximum intensity in double slit diffraction pattern. So, the points separated by a distance a plus b in the two slits are known as corresponding points. So, the condition for maxima given by the above equation simply states that for maxima the path difference between the parallel diffracted ray from any pair of corresponding point in the slit should be even multiple of lambda by 2. The whole number n represent the order of interference maximum. The position of 0 intensity in the interference pattern are given by those value of gamma which satisfy cos square gamma is equal to 0, that is gamma is equal to plus minus n plus half pi. Thus, the minima occur at angle theta such that a plus b sin theta is equal to plus minus n plus half lambda, or d sin theta equal to plus minus n plus half lambda, where n is equal to 0, 1, 2, 3. This equation simply expresses the condition that for minima the path difference between the parallel diffracted rays from any pair of corresponding point in the two slits should be odd multiple of lambda by 2 on reaching the focal plane of the focusing lens. Now, let us discuss the missing order of interference maxima in the double slit diffraction pattern. If the slit width b is kept constant and the separation between them, that is d, is varied, then from the equation a plus b sin theta is equal to plus minus 1 n lambda, it is obvious that the distance between two consecutive interference maxima varies and the size of diffraction pattern due to single slit remains constant. A study of the resultant diffraction pattern so obtained revealed that certain orders of interference maxima are missing. Let us suppose that for the same value of theta, the following relations are simultaneously hold good. B sin theta is equal to plus minus m lambda and A plus B sin theta is equal to plus minus n lambda. The first equation expresses the condition for 0 intensity in the single slit diffraction, while the second equation expresses the condition for a maximum in the interference pattern. Therefore, the interference maxima will be absent in this direction theta. From the above equations, we can write A plus B divided by B is equal to n by m. Since n and m are integral numbers, the ratio A plus B by B should be the ratio of two integers for missing order. The ratio A plus B by B determines the order of the missing interference maxima. For example, if A plus B by B is equal to 2, then n will be equal to 2 times m. Now, giving the m integral values, we get the corresponding values of missing order n. So, if we have m is equal to 1, 2, 3, 4, 5 etc., then n will be equal to 2, 4, 6, 8, 10 etc. Thus, there will be 3 interference maxima within the central diffraction maxima. Similarly, if you have A plus B by B is equal to 3, then n will be equal to 3 times m. Therefore, when m is equal to 1, 2, 3, 4, 5 etc., then n will be equal to 3, 6, 9, 12, 15 etc., and these value of n correspond to missing order. Thus, in this case there will be 5 interference maxima when the central diffraction maximum within the, so thus there will be 5 interference maxima within the central diffraction maximum. In this way, as the ratio d by b increases, the number of interference maxima within the central diffraction maximum also increases. The physical explanation of missing order is as follows. Consider for an example the missing order n is equal to 2. The point on the screen where we expect this order is just 2 lambda further from the center of one slit than from the center of the other. But since slit width is same as opaque region between slits, this point is one wavelet farther from one edge than the other edge of the same slit. Consequently, the secondary wavelets from this slit produce 0 intensity at this point. The same is true for the second slit. Thus, it is obvious that the resultant intensity at this point due to the resultant of each slit will be 0. That is, the second order maximum will be absent. This figure shows the intensity curve for double slit diffraction for the case A plus B is equal to 3 times B and explain the missing order 3, 6, 9 etc. in the diffraction pattern. So, let me summarize what we have discussed till now in this lecture. So, first I explained what is diffraction, and then I explained the diffraction pattern of single slit. So, there we saw that in the single slit diffraction pattern we have a central maxima where almost all light incident light is confined, and this central maxima is surrounded by many secondary maxima of decreasing intensity. Then I describe the double slit diffraction patterns. So, in the double slit diffraction pattern is determined by two terms. First term is the single slit diffraction pattern, and then there is a interference term coming in the final expression, which describe the intensity pattern of double slit diffraction patterns. Thank you.